Today, you will learn about stars. More specifically, the constant process of formation they follow throughout their lifetime. But before I talk about stars, I have to talk about gas. No, not that type of gas. When you look up in the night sky, there are thousands of visible twinkling stars. If you're in an isolated location, you may even be able to spot a nearby galaxy. But for the most part, the celestial sphere is a black background populated by a couple thousand tiny lights. Although it may seem like a barren void, a dark chasm between the stars, the empty space you see is populated by tiny particles of gas, like hydrogen, and dust. Think soot or ash. Although this space, sometimes called the interstellar medium, may look empty to the naked eye, these clouds of particles populate all the empty space between stars in our galaxy. The majority of interstellar clouds are gas, with only 1% of the mass being comprised by dust. When you take just a few atoms, the gravitational attraction between them is not enough to overcome random thermal motion. But take a large cloud of particles, millions of solar masses in size, triggered by either the shockwave of a nearby supernova or just sheer size, and gravity begins to pull them together. As these particles gravitate towards each other, a condensed interstellar cloud, also known as a nebula, begins to form. A nebula, also known as a star nursery, is a general term for a cloud of gas and dust visible as either a bright patch of sky or a dark silhouette against a brighter background. Many nebulae are visible with the naked eye. One of the most known is Messier 42, also known as the Orion Nebula. But there are many different types of nebulas, and many aren't visible without the use of a telescope. Regardless, nebulas are pivotal to stellar evolution. As a nebula contracts, it begins to fragment into individual clouds of gas and dust. Each fragmented cloud, depending on its mass, has the chance to become a full star. As the nebula continues to contract, the individual cloud fragments separate and condense individually. A cloud fragment can be roughly 1 to 2 solar masses and up to 100 times the size of our solar system. As the fragment collapses under its own gravitational pull, the outer layers are released into space, while the center of the cloud begins to heat up as the cloud starts to rotate. If the fragment does not have at least 0.08 solar masses, it will not have enough mass to condense into a protostar and instead becomes a brown dwarf, or a failed star. There's a common misconception that Jupiter is a failed star, when in reality its mass is less than 0.1% of the Sun's. If the fragment exceeds 0.08 solar masses, it eventually condenses to the size of our solar system, and a dense core begins to be forged as the cloud starts to rotate. As the core reaches 10,000 Kelvin, a flattened protostellar disk materializes from dust around the core, and a visible surface, or photosphere, is created. The fragment is now considered a protostar and makes its first appearance at the top right of the HR diagram. The only visible light emitted at this stage is a product of the immense heat and pressure of the contracting center, and as it continues to contract, the luminosity increases. As a result of accretion and magnetic fields, protostars can also eject material through the poles, called protostellar jets. At this time, planetary formation also begins, as material in the protostellar disk combines into larger bodies of matter. As the protostar continues to evolve, it heats up past 1 million Kelvin, too cool to ignite a nuclear reaction, but hot enough to make it thousands of times more luminous than the sun, due to its continued contraction. On the HR diagram, the protostar begins to follow the Hiyashi track, a path distinctive of future main sequence stars. At this point, the protostar starts to decrease in luminosity as temperature skyrockets. The protostar continues to shrink in heat, with core temperatures reaching upwards of 5 million Kelvin as it gets closer to becoming an actual star. The key step that separates caramel from caramel, tomatoes from tomatoes, men from boys, and stars from protostars comes when the core temperature reaches 10 million Kelvin. It is at this extreme heat and pressure, 10 million years after the start of its formation, that a special nuclear reaction can finally take place. No, not that nuclear reaction. 10 million Kelvin is the temperature at which nuclear fusion can occur, wherein hydrogen nuclei split into helium, releasing immense amounts of energy, mainly in the form of heat and high-energy gamma rays. In stars, this is called the proton-proton chain, or PP chain, and is the primary energy source for stars like our Sun. Over the next 30 million years, the star will alter slightly, with the core reaching 15 million Kelvin and the surface reaching 6,000 Kelvin. At this point, the inward pull of gravity and the outward push of pressure from the core are balanced, and the star has reached hydrostatic equilibrium. Now from here on out, the rest of a star's lifetime is entirely dependent on the mass it had as it was forming. The larger a star, the quicker it burns its fuel and the shorter its lifetime. Likewise, medium stars like our Sun live much longer. So let's talk about medium stars first. Medium stars will spend 90% of their lives on the main sequence burning hydrogen for billions of years. But as the core runs out of hydrogen to fuse, hydrogen ignites in a shell around the helium core, causing the dying star's outer layers to expand. As it expands, it cools, with its radius nearly tripling as it moves horizontally across the HR diagram. The helium core contracts as the outer layers continue to burn hydrogen, and the radius expands to roughly 100 times that of the Sun as luminosity increases over a course of 100 million years. When the core reaches 100 million Kelvin, helium is ignited in an explosive flash and helium fusion begins. Via the triple alpha process, helium nuclei are fused into carbon in the core while hydrogen continues to burn in the outer layers. When core helium is depleted, stellar winds drive the outer envelope outwards as the star continues to fuse around the contracting carbon core. The star ejects its outer layers, forming a planetary nebula of outward expanding gas. Ultraviolet radiation released from the hot carbon ionizes the gas, illuminating this outbound cloud. Over thousands of years, this cloud is released into the interstellar medium and is responsible for the heavier elements such as carbon found throughout empty space.
Ow! I crafted the guy that created the planet you're standing on.
Yeah, and I made the stars that became the carbon in your mother's ovaries.
I didn't ask to be born.
What's left behind is a dense, Earth-sized core comprised of carbon and oxygen that no longer undergoes fusion and will cool for the rest of its life, only emitting light through its residual heat. White dwarfs eventually cool into black dwarfs, but because white dwarfs live for billions of years, we have yet to see one complete its life, as the universe is too young, only 13.8 billion years old. Now let's talk about high-mass stars. While medium-mass stars like our Sun will sit on the main sequence for billions of years, a high-mass star with 10 solar masses might only stay on the main sequence for 10 million years. This is because the intense pressure and extreme temperature cause hydrogen to be burned up much faster. High-mass stars follow the same initial expansion as medium-mass stars, but as core hydrogen runs out and fusion shifts to a shell surrounding the core, it expands into a supergiant, with its envelope swelling and cooling. There are many stars, such as Betelgeuse, which are currently undergoing this stage of stellar evolution. Much like the work done during this project, a little bit was done here and there along the way, but the most important steps were taken in the final stretches. Hydrogen fuses to helium, helium fuses to carbon and oxygen, and so on. For a massive star, iron accumulates in the core, but because iron fusion absorbs energy, the point at which it can occur signifies the end of a star's life. Therefore, the core becomes unstable and begins to collapse. Now, depending on the star's mass, one of two things can happen. As the star collapses, a catastrophic rebound is triggered and a massive amount of energy and gas are released in a supernova. A supernova completely destroys the star, and there are two types that can occur. Type 1 supernova occur in binary systems when a white dwarf exceeds its mass limit and explodes. Type 2 supernova occur as the result of the core collapse of a massive star, where the outer layers are ejected into space and a superdense core is left behind. Now, you may be asking, why does this matter? Nebula, supernova, what's the big deal? Well, here's where high-mass stars differ in final form. If the star's core mass is between 1.4 and 3 solar masses, the collapsed remnant becomes a neutron star. Neutron stars, named because they are almost entirely comprised of neutrons, are small, roughly the size of Manhattan, usually around 20 kilometers wide. Neutron stars are special because they are extremely dense, about 10 to the 17th power kilograms per cubic meter, so a sugar cube's worth of neutron star could weigh roughly as much as Mount Everest. Neutron stars can also emit energy through pulsars, or rapidly spinning beams of electromagnetic radiation. If the star's core is greater than 3 solar masses, it collapses into a black hole, an object with gravity so strong not even light can escape. While we don't know much about black holes, we know they mark the end of a massive star's life and are one of the many mysteries of the universe. Now, hopefully at this point you're wondering how this all relates to itself. After all, It is a cycle, not a single path. The gas and particles released from nebulas and supernovas are what end up populating the interstellar medium and, when concentrated, form nebulas, completing the cycle. The shock waves from supernovas can also sometimes act as the trigger for fragmentation and creation and the start of new stars. So hopefully you learned something today, and I hope you leave with a better understanding of stellar evolution.
And remember, helium is not just something fun to inhale.